We are talking about finite and algebraic extensions, and we want to keep talking about these simple looking algebraic extensions. Let me remind you a little bit. K over F denotes a field extension. When you have a big field K containing a smaller field F, the bigger field becomes a vector space over the smaller field, so it has a dimension, maybe infinite. This dimension is called the degree of the extension. A finite extension means that this dimension is finite. We have a theorem that says that if you have a tower of extension, so one field contained in another field contained in another field, then the degree of the big extension is equal to the product of the degrees of the smaller extensions. So in particular, if the smaller extensions m over k and k over f are finite, then the big extension is also finite. Then we have this all-important definition of algebraic elements, generalizing algebraic numbers. An element a in K is called algebraic over f if there is some non-zero polynomial with coefficients in f such that p of a is 0. So a satisfies some polynomial equation. So for example, root 2, 2 to the 1 over n, e to the 2 pi I over n. These are all real or complex numbers. These are algebraic over q. Root 2 plus root 3, I can write a bunch of things. Yeah, so maybe let's find a polynomial equation that this satisfies. So you take a square, then it's 2 plus 3 plus 2 root 6. So s square minus 5 is 2 root 6. So s square minus 5 square is 6 times 4, 24. So a to the 4 minus 10s square plus 25 is 24. So a to the 4 minus 10s square plus 1 is 0. Here is a degree 4 polynomial that this number satisfies. So it's an algebraic number, etc. So you have such algebraic numbers versus pi, e. These are famously non-algebraic. We are studying this sort of numbers, but in abstraction. We say an extension is algebraic if every element of the big field is algebraic over the smaller field. Algebraic extensions can be very big. In fact, if you take all numbers, in all complex numbers that satisfy some polynomial equation over Q, like all these, those are called algebraic numbers. So if you take the set of algebraic numbers, call it A maybe, so this is some subset of C, this is actually a field. And by definition, everything here is algebraic over Q. So A over Q is an algebraic extension. But this is not a finite extension. This is infinite. The dimension is very infinite. Okay. But the converse is true, actually. So algebraic extensions don't have to be finite, but finite extensions are almost trivially algebraic. I sort of rushed through the proof last time, so let me say this again. So that K over F be algebraic, be finite, which means K is a finite dimensional vector space over F, and take some A in the big field. Then the observation is that if you take all these elements, 1A, its square, etc., cannot all be algebraic, all be linearly independent. Over F, because we have all these elements in K. You cannot have infinitely many linearly independent elements in a finite dimensional vector space. Means what? Means between these elements there has to be a finite dependence relation. So there's some C0 plus C1a plus C2a square plus etc. plus Cn a to the n has to be 0 for some C0 Cn in F and some Cj non-zero. That's what a non-trivial dependence relation looks like. So now let Px be the polynomial C0 plus C1x plus Cnx to the n. This is a non-zero polynomial because some Cj is non-zero. And A satisfies it by our construction. So A is algebraic. So every element in K is algebraic. Let's say I have a algebraic extension and you just take one element in there. And you look at the field that you get by adding just this one element. So these are sort of the simplest kind of algebraic extensions. So let K over F be an algebraic extension, and let A in K. What I want to study is this thing, F round bracket A. What it means is the smallest subfield of K containing F and A. It's also called the subfield generated by subfield of K generated by F and A. So you take all subfields of K that contain F and A and intersect them all. That will be the smallest subfield of K that contains these guys, and that is denoted by F round bracket A. For example, if you take a transcendental number like real number, and the real number pi, and if you consider this extension, Q round bracket pi is going to be just all such expressions. All such numbers, where the denominator is non-zero and AJ, BJ are rational. You can check that by hand. That's the smallest subfield of real numbers that contain both rational numbers, all rational numbers and pi. So, except the difference is here A is algebraic. So A does satisfy some polynomial equation. So what I'm looking at is that I have some extension field and I have an element here that satisfies some polynomial equation. Satisfies a polynomial over F. So I want to understand what the field that you get by adding solution of a polynomial equation, how does it look like? Okay, so I want to know how this looks like. I'm going to need another notation. F square bracket A is going to be the subring of K generated by F and A. Meaning it's the smallest subring of K that contains both F and A. Again, if you take this example, then it's just going to be all such polynomial expressions. You don't need denominators now. All real numbers that can be expressed like so. Yeah. Again, the difference is we are not looking at an algebraic number. And to understand this, the structure of F round bracket A naturally leads you to this notion of minimal polynomial. And this whole discussion, I haven't isolated out theorems here, because this whole discussion is absolutely crucial, and I want you to sort of retain this whole thought. Some of it is definition, some of it is argument, but this whole discussion needs to be absorbed in its entirety before you sort of proceed with this subject. So please repeat this if you want, but digest this completely before you move on. So I'll call this minimal polynomials. It's not long, it's It's not a very long train of thought, but sort of every step is very important. So you have an algebraic extension, you have an element in the big field, and you want to understand the field that you get by adding this one element to F. Okay. So we'll look at it next time.